So let me do this question. This is one of the few questions that I haven't done yet. And looking at it, it looks like it's not the easiest question. So I really should have done it earlier. Sorry, I'm only getting to it now, but let me finally do it. So the question asks, calculate the induced electric field. So we are going to be dealing with the Faraday's law. Let's draw a picture of the setup. So it's some number of turn coil with some diameter placed in a uniform magnetic field, so that the face of the coil and the magnetic field are perpendicular. Okay. I don't know why the question didn't draw the picture for us, but that's fine. Let's draw the picture ourselves. We know how to. So let's just start with the picture of the coil. I'm gonna position it so that it's, well, let me position it so that it's kind of lying horizontally. So you imagine coil just sitting on some desk, or I guess more likely hanging from some stand. So you got the coil, and we'll just say it has some n turns, and it's a circular cross section. It'll have diameter given in the question, and we need to specify the magnetic field. We are given some magnetic field for the region. We have the magnitude, and it's uniform magnetic field. And the question is saying this amount of magnetic field in 0.1 second will go to 0. So as you might have guessed, both from the chapter it's in and the word induced electric field, this is a Faraday's law question. So let me start by stating the Faraday's law. Faraday's law says it looks very similar to Ampere's law. It involves a line integral around the closed loop of a field, this time electric field, E dot dl. And that's equal to minus the time derivative of, and in the form that we stated, it's the time derivative of the magnetic flux. And as a reminder, we defined the magnetic flux using the B dot A. So in a most general case, it would be the surface integral, not necessarily closed, it could be open, of B dot dA, whatever the surface is that we are dealing with. So here in this question, actually, this is a topic that deserves careful consideration. What surface is it that we are dealing with? And I guess if you thought of this surface that's kind of enclosed by this wire, if you think of it as this kind of surface, I'll say it'll give you the right answer. You could think of this enclosed surface as basically a single circular surface of the diameter d times the number of turns. Like if that's your mental image and or your model, how you're calculating, great, that's fine, that works, we'll give you the right answer. Now, if you are wondering how does that actually work, well, you kind of have to imagine that wire, the surface it bounds is actually pretty complicated looking. It's folding on itself, and this single ray of magnetic field goes through that surface basically multiple times in the way it's folded. It'll go through it n times by the number of turns. So if you think of this surface as basically circle times n, great, that gives you good enough of an answer, and the kind of visualizing that actual surface bounded by actual coil, I'll leave that to your spatial imagination. So I think it's worth probably writing down the expression for the magnetic flux so that we can put it into this expression here. So the magnetic flux should be, now if we think of it as a circular surface, then it's just going to be the magnetic field times the surface of the single circular area, pi times, since we have the diameter, let's say d over 2 squared, and then we are just going to multiply by n to account for n number of turns. So this expression on the left, it gives you the induced voltage. And now if the question had asked simply for the voltage, we would leave it there. But it is asking for electric field, and that could be somewhat complicated. So I think I want to write a kind of a simple expression in this sense. So this E dot dl that we have. Before I go further, let me just correct that this is not the magnetic flux full expression, but just at the start, B naught. It's this field here. It's going to be going to 0 in this amount of time. So let me make sure I note that. Now, this electric field here, so what Faraday's law actually gives us is the total voltage, but we can make some reasonable assumptions, like maybe the field is uniform along the length of the wire. Then, okay. If I were to assume that, which I'm not sure if I'm 100% justified, but I think it's not totally unjustified. So I'll just say, okay, it's gonna be basically this integral will be basically the electric field times the what I'm gonna call total length. So that total length, we gotta figure it out. So it's going to be basically the boundary version of this. So it'll be circular circumference times n. So it should be the electric field times the 2 pi r, or I guess since we have diameter, let's just say pi times the diameter times the number of turns n. So with that, let's build the final expression that will write our answer with. Let me just move some stuff and make some space here. So I think given the type of information we are given, it'll be simplest to, instead of doing, calculus or derivative and whatnot, just deal with the differences. So we'll say the left-hand side, that would end up being electric field times the total length is equal to, now for right-hand side, I'll do two things. One, I'm just gonna deal with the absolute values. So this is just going to be the absolute value, and on the right hand side I'll want to deal with the minus sign, absolute values. I don't think it's asking for me to get the directions anyway. And instead of writing the time derivative of this, I'll say change of the magnetic flux over the duration of time, because then this fits neatly into the information I'm given. The change of magnetic flux is the final flux, which will be 0, minus the expression for flux that we have here. B naught times pi d over 2 squared times n divided by amount of time, 0.1 second minus 0. When it's starting an absolute value, I don't really care about the sign. So I guess with the two minus signs, it would have come out to be positive, but I don't think we have to deal with that. I do see some nice cancellations, so let's take advantage of that. I see pi canceling, great. I see one factor of diameter canceling, all right, let's use that. I'll make sure that I don't forget that this should be 4. And this is, I think, the most wonderful thing. N cancels. You actually don't care how much coil there is, as long as you are concerned only with the electric field. Whether it's 1 turn or it's a million turn, the electric field will end up being the same. Now the voltage might be different, but electric field, the N just cancels. There is a dependence on the diameter because I guess it determines the area. So let me write down the simplified version here. It's gonna be electric field is equal to, let's see, I got just the B naught times D divided by 4. B naught times D divided by 4. Again, I'm taking absolute value. Divided by the amount of time we were given, 0.1 second. I don't know why I had that as numerical value, but let's plug in the numbers and make sure I didn't make any mistakes. B naught, 0.5 Tesla times the diameter, 13.5 centimeter. And because I'm using Wolfram alpha, I'm just going to let Wolfram alpha convert units. Divided by 4. I didn't need to use 57 turns because n canceled out. Divided by the amount of time, 0.1 second. Yeah. Magnetic field is cylindrically symmetric. I don't know if I needed that. I mean, it's uniform. Maybe this is meant to be electric field, or I'm not sure. That last sentence seems unnecessary, especially the uniform magnetic field. But well, so I get the electric field. Oh yeah, volt per meter. That's right unit. 0.169. 0.169 volt per meter. So that's it. What was most time consuming is making sure we have the right understanding of the setup and recalling and applying Faraday's law correctly. The algebra itself is simple.